So reaction mechanism 10, we're almost at the halfway point here. And in this case, we're going to begin seeing some reversals of reactions that we've seen before. So just to kind of give an overview here, let me go ahead and draw an acetal. So again, this is an acetal, and we're converting it into a hemiacetal. So some things to highlight here, right? We can see in this case, we have two ether connections to a central carbon atom. So again, that makes it either an acetal or a ketal. And we're looking at this group here to see that we would have come from an aldehyde, so this is an acetal. If these were two R groups, meaning that this carbon was originally part of a ketone, again, this would be a ketal to a hemiketal conversion. At the end of the day, looking at what's different here is we have the essentially interconversion of an OR group for an OH group. And when we were going in the forward direction here to take and convert an OH group into an OR group, again, the chemistry was that we made this into a good leaving group by protonating it, generated a very electrophilic intermediate, and allowed our leaving group to departure by using the lone pair of electrons on this adjacent oxygen atom. And so we're going to see the a very similar process here, where essentially we would like to make this guy be a good leaving group, so we'll protonate him. Lone pair on this adjacent hetero atom allows us to reform a carbonyl containing intermediate here, allowing our good leaving group to leave, and now that very electrophilic intermediate is going to be reacting with water to generate our product. So again, this is really a reversal of reaction mechanism 7, but again, we're not going to just see a reversal of the steps, but we need to reverse the chemistry. And then again, just to highlight here, most of the times when we're going to be drawing a reaction mechanism from this point forward, you're going to know the molecules you want to make. So again, it's not to say that there aren't other possible avenues for chemistry, we're just not exploring them with the given mechanism. And that's the beauty of a lot of times what happens in enzyme active sites is we are able to dictate the specific chemistry that goes on. Not only the scope of the chemistry, but also the regiochemistry, where chemistry happens, as well as the stereochemistry, specific stereochemistry at, say, a carbon that has 4 different things attached to it. So again, highlighting for this mechanism, eliminating the molecule of the alcohol. So we're first going to somehow make that into a good leaving group. Protonation is kind of the best mechanism to see that happen. Again, so reversing the last step of reaction mechanism 7 was deprotonation of the incoming second equivalent of alcohol. Now we're going to be protonating that alcohol to allow it to be a good leaving group. All right, so hopefully pretty straightforward mechanism here. Let's go through and just kind of highlight the mechanism, and then we'll talk about some biochemical applications. So here again is our acetal. Protonation of this guy, and for future, I tend to use BH to represent an acid molecule that's going to be able to donate a proton, and then and BH as in a protonated form here, so it's positively charged, and then B as a base which can serve to deprotonate. So again, protonation of this guy is going to allow us to generate that good leaving group. So now we've got a decent leaving group here. The lone pair of electrons that are on the adjacent heteroatom are what are going to be allow that leaving group to leave. And again, generating an intermediate that is quite electrophilic. Keep all my R's straight there. And then water is going to come in here. Water, again, not a superb nucleophile, but when we have a pretty good electrophile, because we've made that carbonyl very electrophilic. Pretty easy chemistry that happened there. Keep forgetting all my primes and double primes here. Okay, so now we have this positively charged intermediate, which we can use a base here now to deprotonate and generate our final hemiacetal neutral intermediate. So a few comments that I've noticed that I keep writing on people's reaction mechanisms are when you are showing arrows always start at electrons, so that's either going to be a lone pair or a bond, and then we generally draw these arrows either to atoms or to make new bonds between two atoms. So just make sure anytime you're drawing an arrow, it should either start at a lone pair of electrons or it should start at a bond, which represents electrons, because we're showing the movement of electrons, so we need to show where those electrons come. Otherwise, you really don't need to show bonds, draw out bonds, or draw out lone pairs. But again, if they are going to be part of the reaction chemistry, the movement of electrons, we do want to see them. So again, a couple of other comments here and kind of a context for this in terms of biochemical application. This is truly a hydrolysis reaction. Let's flip back here for a second. We actually see water coming in, and at the end of the day, water is going to be facilitating the lysis or the breakage of this bond. So the reaction doesn't explicitly say hydrolysis, meaning that we add water to the system to break something or lyse something apart. But again, if we think about how reaction mechanism 7 worked, that was a condensation reaction, and we generated that acetal by eliminating water to make room for a second equivalent of alcohol to be added. So again, that was a condensation reaction, and we talked about how that's used to first cyclize and then polymerize sugars through the generation of that glycosidic bond. So again, the first reaction mechanism in generating the hemiacetal or the hemiketal was to use to do chemistry to cyclize sugars, and then the formation of an acetal or a ketal is used for polymerization. So again, highlighting that again, acetal and ketal formation is how we polymerize sugars from their cyclized form. Again, that reaction is called condensation since we eliminate water, and so that new bond that we form is a glycosidic bond. And so this chemistry really highlights what happens in the reversal of this process. That is the breaking of glycosidic bonds to generate cyclic monomeric sugars via the use of water. And so again, this chemistry is going to be what we see when we look at chemistry for the hydrolysis of sugars. So kind of giving a future sort of preview, when we study kind of enzyme chemistry, we're going to address hydrolysis reactions that we see in all biopolymers. So carbohydrates, we're going to see hydrolysis of glycosidic bonds. Proteins, we're going to see hydrolysis of peptide bonds. Nucleic acids, we'll talk about hydrolysis of phosphodiester bonds. And we'll also talk about triglycerides, not really a polymer, but we're going to talk about hydrolysis of ester linkages in these molecules. So what's really interesting is carbohydrates, proteins, and triglycerides are all dietary sources of fuels. And so this chemistry is what has to happen in order to get these species out of your GI tract and into your bloodstream. So we'll spend a lot of time talking about the metabolism of these fuels, but hydrolysis of this glycosidic bond generates our cyclized monomeric sugars. And again, a key theme when we talk about dietary fuel metabolism is that only monomeric forms of fuels are able to exit the digestive system and enter the bloodstream. So we'll talk about this also in the context of something called leaky gut. And so, again, your immune system is only designed to recognize these monomeric forms. So if you have larger pieces of either carbohydrate, protein, and to a much smaller extent triglycerides, but again, those other two tend to be immunogenic in terms of their response if you're getting these big parts in, and that is kind of a consequence of what we refer to as leaky gut. So we'll talk about that in subsequent lectures. So breaking these polymeric linkages is an essential part, a component of properly obtaining fuel from dietary foods.